Introduction to Heat Treatment. Vocabulary. Gary A. Pace, P.E., CWI, Katy, Texas. All right, so we're going to talk about some of the grain structures and some other vocabulary. So one of the first ones we're going to talk about is ferrite. Ferrite is just the purest form of iron. There's nothing else in it. It's just body-centered cubic phase of iron. It's really soft. Iron is a very soft material when compared to other steel microstructures. Ferrite is super, super soft. That's why we have to add carbon to it to get the mechanical properties we're looking for. So this forms at really low temperatures and low carbon content during slow cooling. So if we don't have enough carbon in there, we're going to get mostly ferrite. Carbon content, well, when we're talking about carbon content, we're talking about what's the percentage of carbon in our iron carbon alloy. You get up to 3 or 4%, you're looking at cast irons. And a 0.15 or a 0.2 is a reasonably, low, medium carbon content steel. So carbon, like I said, is the main driver that affects the properties, the mechanical properties of steel. The two main ones that we're looking at are strength and hardness. But carbon content is the driver of this whole system, this iron carbon system. Martensite. If you've been around steels and whatnot, you're going to hear this term, martensite. This is the body-centered tetragonal form of the iron carbon structure. And it is allowed to form when austenite is rapidly cooled. So this is, let's say we've got a chisel. Our blacksmith is making a chisel for us. So he heats our part up to really, really hot, gets it above 2,000 degrees, turns it all into austenite, which is face-centered cubic, and then he dumps it into the water. And once he dumps it into the water, that chisel, the crystalline structure goes from face-centered cubic to body-centered tetragonal. And that's what we get here. It's a very hard, brittle microstructure, and it's got this needle-like appearance. And we're not going to super deep dive into this, but if we're doing an introductory course on heat treatment, we would be remiss if we didn't at least touch base on some of these microstructures. And this martensite is formed when we're quenching or rapidly cooling from the austenitic phase. We're going from face-centered cubic, which, a couple thousand degrees, and then we're plunging it into water, and then it's going to body-centered tetragonal, and we're going to get martensite. Bainite, we're not going to talk too much about this, but you might run across this in your professional travels. This is when we cool the material from a face-centered cubic to a body-centered cubic at a somewhat moderate rate. We're not plunging it into the cold water super quick to get it to quench and get a really martensitic structure. We're shooting for bainitic. It's got a lot more toughness than martensite. Martensite's very hard, but it's brittle. And this occurs at temperatures above the martensite formation, but below perlite range. So this is a really good microstructure for a lot of applications. But we're cooling it slower than we would if we just quenched it. So we've got the critical temperatures of steel. You might hear this one. It's a point at which steel undergoes a phase transformation. So that's when we go from body-centered cubic to face-centered cubic. Or austenite to ferrite. It's when we change phases. Our crystalline structure changes. We need to have knowledge of the critical temperatures for heat treatment processes. This is super important if you're going to be doing this for a living. Machinability, when we talk about machinability, how easily can we machine this material? How easily can we put it on a lathe and cut it? How easily can we deal with this stuff? Is it miserable material to deal with, or are we able to machine it and not have too many problems? So with steel, the steel composition, the microstructure, and the hardness all are going to affect the machinability of this material. Austenite. Here's another term for us. Austenite. This is steel in a face-centered cubic structure. You can see it right there. That means we've got an atom on every corner, and then on each face of the cube, we share an atom with the next cell over, the next cube. So austenite transforms into other microstructure or crystalline structures when we cool it. So austenite will go from face-centered cubic to body-centered cubic when we cool it down. Or if we cool it really quick, it'll go to body-centered tetragonal, which is martensite. And a lot of this is dependent on how much carbon we also have in the material as we cool it. If you look at a phase diagram, this convoluted diagram is an iron carbon phase diagram. And when you look at it right there, the arrow is pointing that where it's kind of just a solid semi-green color. That is our austenite range. It means that we've heated our material up and our material has gone from body-centered cubic into face-centered cubic, and it is just austenite at this point. This is going to tell us the temperature window for various heat treatment processes. What do we got to do to get our material to react and give us the mechanical properties that we're looking for when we heat it up and cool it down? Ductility. This is the ability of a material like steel to deform plastically without fracturing. It's like if I take a copper wire, I can bend it. We don't build wires out of cast iron because it would be way too brittle. But something like aluminum or copper have great ductility, and we can use these materials in certain situations. But ductility is a material property that allows a material to be bent and not break. A lot of plastic deformation before failure. Weldability. This is one that's close to my heart. The definition of weldability is how easy is this stuff to weld? Your garden variety carbon steels are pretty weldable. They don't have a lot of carbon in them or a lot of other alloys that are going to give you issues, but there's other materials that are just absolutely brutal to weld. There's a stuff called P91. It's, I don't know, 9 chrome, 1 vanadium, I think, and this stuff is just nasty to weld. It is not for people that are newcomers to the welding workforce. This stuff is because you got to preheat it a lot, and then when you cool it down, you've got to add a lot of heat to it. Then you let it sit for a while, then you do a hydrogen bake out so you don't get cracking, and then you send it to the heat treater, and then they cook it for a while. So it's just nasty. But it's not a very weldable material. You really got to have your act together if you're going to weld that material. So a lot of the considerations for this are, steel composition and microstructure. They influence the weldability of a material. Questions, comments, thoughts, concerns? Gary A. Pace, PE, CWI, Katy, Texas.